So now that you understand how hierarchical clustering works, let's take a look at a bit of a more complex clustering mechanism known as k-means clustering. So k-means clustering is again a hard clustering method, meaning that a data point is either within a group or another group. There is no probabilities or percentages. A data point is either part of a group or it is not part of a group. So it's an iterative method, and it eventually splits data into k clusters. Note that k is predefined beforehand. So you can tell this algorithm, I want my data to be split into 3 clusters. In this case, k would equal 3. If I wanted to split into 5 clusters, k would equal 5. It's much faster than hierarchical clustering and is one of the most widely used algorithms. The data, however, must be comparable by Euclidean distance. It'll become apparent why, and each cluster is radial, meaning that it spans a certain radius in n dimensions. In the case of 2 dimensions, this would mean that our grouping would be in circles. In case of 3 dimensions, it would be spheres, but it's limited to a certain radius. So let's get onto the algorithm. So there are 6 key steps. First, you have to define the number of groups you want to choose from. So in this case, k could equal whatever number you want. Then second, we randomly assign k centroids. We'll get onto what centroids mean a bit more later, but for now, they're the centers of our groups. Then 3, we'll classify each data point as a member of a certain group. Then we'll update the centroids based on the mean values or mean positions of the groups. And we'll keep updating these centroids until they don't change anymore or they converge. Then we'll measure how well this model has fit the data. And then we'll repeat this whole process for however many times we want with different models using the same k. And we'll choose the model that ended up with the best fit to the data. That was quite a lot to take in, so let's go through this process step by step, starting with defining k-groups. So we'll be using k-means on a mailing list dataset. By grouping the data, we'll hopefully try and find out certain groups of consumers and isolate certain behaviors. This could be useful in the case that we're given a certain amount of money to spend as owners of a business, and we want to try and spend that money in advertising to the relevant consumers. By clustering these consumers, hopefully we can realize what groups will get the best, what groups will be worth the advertising and what won't be. Currently, the optimum values of the groups is unknown to me. I don't know if I should group the consumers in 3 groups or 5 groups, but for now, we'll just have a look at the data. And later on, we'll talk about techniques to find the best values of k to use for certain data. So here is a rough idea of the data we're dealing with. I've organized the consumers by their spending score and their annual income. And as far as I can see, there are 5 clear groups I can find. People who spend a lot but don't have high income, people who spend a lot and have a high income, and continued, and so you have top left, top right, bottom left, and the middle group. So I'm going to say k equals 5 for my model. Then we can start assigning centroids. So what is a centroid? Centroids are the centers of our clusters. Given our clusters are circular, there has to be one unambiguous center, the kind of center of our circle. Initially, these clusters will be randomly assigned in the data. Other centers exist like k-medians or k-medioids, but we'll be using centroids. Remember, centroids are the centers of our clusters. In this case, we have a red cluster. The centroid is shown in the white, and we have a blue cluster, and the centroid is shown in the white respective there. Remember, they're radial, and the centroid is the center of our cluster. Now we can start classifying data points, given our centroids. For each, first we randomly assign the centroids. So we pick a random data point in our dataset, shown before. We pick a random data point, as shown at the bottom, and then we choose it as the center. And then for every other data point in our data set, we'll figure out what class that data point belongs to. To do that, we'll take the distance between that data point and the closest and each centroid. So in this case, we have two groups, k equals 2, and we say, okay, how close is it to the red group centroid? And how close is this data point to the blue group centroid? The data point we're talking about here is the point in clear white. So those distances represent how close that point is to the red group and how close that point is to the blue group. Then, depending on the smallest distance, that group is classified as that data point is classified as that group. So in this case, the red distance is much smaller than the blue distance. Therefore, that white data point would turn red and be classified as part of the red group. Remember, we're using the Euclidean distance as the distance metric. That is to say, for however many dimensions our data is in, we just simply take the difference of each dimension, square that, and then square root it. So in the 2D case, that's just Pythagoras theorem. Since we have x dimensions and y dimensions, we take the differences, square them, and then add them and square root it. So you do the exact same here. You take the distance horizontally and vertically and take the smaller one. Okay, so after classifying each data point, we can start to update the centroids to better positions. So first of all, let's classify everything. So remember, we take the smallest, we classify it as to the closest centroid. So after we do that, we end up with something looking a bit like this. We have the red data points and the blue data points. However, since this has been randomly assigned, this obviously isn't the best clustering for configuration. What we do after we classify all the data points is we take the mean average of each data point within the cluster and set the centroid of the group equal to this mean. That is to say, if I was looking at the red group, I'd take the sum of all the red group coordinates and find the mean position of them. When I find that mean position, I will move my centroid to that position. But as you can see, the means are shown with the white arrows. So the red moves up and to the right, and the blue also moves right and slightly up. Okay? Those are the means of the groups we've just classified. We move our centroids to there, and because our centroids have moved, our groups should update. So then again, we look at each data point and we look at the centroids of each group, and we classify each data point as being a part of each group. As you can see, some of the data points have changed from blue to red. So these were previously blue, but because this red centroid has moved, they are classified as red because they are closer to that centroid. Then we simply find, because some data points have changed categories or classes, we have to find the mean of the new classes. So because of the new data points, the red mean would be slightly higher, whereas the blue mean would be slightly more to the right. We figure these new means out, and we move the centroids to these places. Again, because the centroids have moved, we reclassify data. We move the centroids accordingly one last time. And you might notice that the centroids hadn't moved that last time. There were no changes within the data. There were no new data points that were reclassified. The centroids stayed in the same position. At this point, we can observe that they haven't changed. Therefore, they have converged and reached their final state for this model. As you can see, there's a clear distinction between the red group and the blue group, shown by the gap. And it looks pretty good. We've reached the final state for our model. The model is converged. However, there's a key idea behind the k-means clustering algorithm. Because we've started with random centroids, how do we know that those random centroids haven't led to a bad final configuration or a good final configuration? How do we know what states are the best? We need some kind of metric to see how well our model fits the data. So as you can see on the left, this model started with a different configuration for initial centroids, and the model on the right started with a different initial centroids, and they've reached to two totally different groups. Okay, how do we know which model is better? We can measure the fitness of a model based on its variance. The variance in this case, or the variance I will use, is the summation of the Euclidean distances from the centroid, or the center of the group. The lower the variance, the better the fit. So in the example of the red group, I take the centroid and I take each data point and I figure out the distance from the data point to the centroid of the class it represents, or the group it represents. So I've shown that with the white lines. I repeat the process for the blue group. Turns out they're 15.3 units or arbitrary units. I add up the variances for each group and I find out that this model has a 36.7 variance. If we repeat this process with the different outcomes we created for the different initial centroids, then we can eventually pick the model with the lowest variance. This is the best model. You can see why we want low variance, because then the centroids are more aligned with the majority of the data points. As you can see on the left, there's far too much variance with the blue group, and on the right there's far too much variance with the red group. However, with the middle clustering, there's a perfect balance of variance. So earlier on, we talked about using or finding the optimum K, and how for certain data sets, the best K to use might not be very clear. So with this example, it might not have been very clear to you, or even me when I started with this data set, as to what K we should use. So I ended up using K equals 5, but K equals 3 could be another valid setup. So how can we find this optimum K value? So after looking at the data yourself, the next best thing you can do is use the elbow method. What the elbow method does is it will create some random, it will use different values of K on the K-means model, and it will essentially run through this process and kind of brute force it. The idea is we keep increasing K and we keep running different models and we plot the variance of the models. So you can see K equals 1, K equals 2, K equals 3, and we'll produce a graph based on it. At some point, like obviously the variance will reduce as K increases, but at some point the data will start overfitting. And at that point, the idea of clustering becomes redundant. We just have a model which for each data point there exists a cluster, which isn't very useful. If any of you have done some economics, you'll be familiar with the idea of diminishing returns. Essentially, the more clusters you'll use, the less bang for your buck you'll get. You want to find the optimum K, and when you graph it, it looks like an elbow within the graph. It's a bit of a steep cut in the graph. There's a smooth curve, and then there's a bit of a cut. You could use some maths to find out the K, but for most of your usage, it'll be easy to find it using your eye. In this example, it turns out that K equals 2 is the best clustering. Other examples, there could be 2 possible elbows, and you could explore each one and use some statistics to figure out what's best, or maybe plot variances. So that's been a lot to get through. So I want you to take a quick break on the Jupyter Notebook and just run through examples using the sklearn data frame and really get to grips with how K-means works. And you can look at some analysis of different models and how they're performed. So I'll let you get on with that.